Hello everybody. So separating variables for first order equations. So still in this case y prime is of this particular form. Our differential equation is first order. And now we're going to look at some special cases where we can use which are not separable equations, but we can turn into separable equations. Now before I do this, let's review a little bit quickly our linear differential equations. So this is linear, so this is from 2.1, right? How did we solve this? Well, we said we first solved the corresponding complementary homogeneous equation. So this was the complementary equation. And once we did that, to find then the solution for the actual equation, we had to find a particular solution. And what we used is we used an equation for this, and so we found a solution. Let's call this YH of homogeneous. So YH is a solution, and we only needed one. That's why we could choose our parameter, our constants, very simple. So we found a solution to this homogeneous equation, which I'm now going to call YH, the homogeneous solution. And then to find a solution here, we need what we call a particular solution, and so I call it YP, P of particular. We suggest that it would be of the form U times YH, and where this U is again a function of X that we can then determine. Sorry. Okay. And that method worked. I've done this several times now, so I'm not going to do an example anymore. And we're going to do this kind of similar things here. So keep that in mind. And here is the first example that I want to look at. These are called Bernoulli equations. Bernoulli, let me write it correctly. Bernoulli is a French mathematician from the 19th century. And you studied first this type of equations, and here's the equation: y prime plus pxy equals fx y to the power n. Well, let me call y to the power r here, because otherwise you might think, oh, it has to be a natural number. No, r can be any number here. So r is some positive real number. Because you can have rational exponents, right? That would be radicals, but you can even have irrational exponents. Now you could say, oh, this is a linear equation, Professor. Look, this is linear. No, because here there's a y part here. That makes it not linear, right? So in linear, you shouldn't have a y part. Here we have a y part. Okay, so that makes it different. Okay, but we're going to use the same method as what we did for separating variables. Sorry, for first order linear equations. So, and the best way is to do this on an example. So here's an example. Let's take the example. Let's take a simple one that we can solve quickly. Y prime minus y equals xy squared. So I repeat, it's not linear because of this y square here. Okay. And I wrote it in this standard form because, again, we're going to use the complementary equation here. It's less well defined, but okay, I'm going to still call it the complementary equation. Is y prime minus y equals 0. No, that one we have solved before, right? Y prime equals y. In fact, we can do this by separating variables. That's what we did. These linear equations, homogeneous, this is now a homogeneous one, right? So this is the homogeneous linear equation. That were separable equations. And let's just do it from the point of view of separable equations. Well, let's solve for y here. So we get dy over y, right? The y goes in the denominator. What happens to the dx? Well, it comes up here and there's nothing else. So we integrate this. This is the ln of y is x plus a constant. Okay, integrating both sides. And then solving for y is by taking exponentials e to the x plus c, and that again is ec times ex, so that is d times ex. So that is the general solution of our complementary homogeneous equation. Now what we said is we're going to use one solution here, a homogeneous solution, and try this particular form here. Okay, so we're gonna we're going to look for a y that is yp. I'm going to write yp here. Yp is of the form u times yh, where yh is what? This is my yh. Okay, but I can take any simple d I want. Of course, I cannot take d equals 0 because that is, I need a non-zero solution. So I can take d equals 1. So for me, this would mean that I'm going to take, and instead of yp, I'm just going to write y now. You have to get used to that because we don't want to write too many things because these y's we're going to have to use all the time, and it gets very illegible if we put subscripts here. So I'm dropping that now, and I'm saying this is what I'm looking to solve. Let me explain where everything comes from. Instead of yp, I just write y. I'm now trying to solve this equation, right? And this equation used y. This equation used y, so why not use the same letter? The u is going to be this new function, so u depends on x. That is something that I don't know yet. Okay, so we propose. So we propose a solution of this form, and the ex, where does that come from? Well, that's what we said. That is a solution of the complementary homogeneous equation, and that is what we put here. So we're looking for a solution of this form. So let me write down the equation again. Y prime minus y equals xy squared. So I'm going to plug this in here. What do we get? uex prime minus uex equals x uex squared. Now don't forget there's now a y on the right hand side too. Okay, so derivative, that's product rule, that is u prime ex plus uex, derivative first, okay, minus uex equals x u squared e to x. Right? I hope that you see how I did the squaring. And we know that what needs to happen in order for this method to work is we need some calculations here. So that part falls away, but we have still a u here. You say, oh, professor, now we're in trouble because what is this thing? But this is exactly what we said we would do. Remember, what we're going to try to do is separate the variables. That was the technique. Meaning we do this trick, or the substitution of this kind of new function u is supposed to get us something that is a separable, where the variables are separated. And this is exactly what happens. Look, I can solve for u, bringing that to that side, and on the other side I get x e to x divided by ex, right? And this is exactly what I want. So let's write it now in a bit nicer form. This is du over u to the minus 2, because I have to kind of integrate, right? Here the e to x and ex cancel. Well, no, cancel. We subtract exponents, so we get x, ex, 2x minus x. And then the dx, of course, because I'm writing now differentials, so that I can integrate. Okay? The integral of this thing is by the power rule equal to that. The integral of this thing, what is that? That's integration by parts. So quickly, integration by parts. So that's why you need to know everything of your calculus, right? The previous example in the previous lecture I showed you about decomposition, partial fraction decomposition. Here you use integration by parts. So how does that work? We had that integral u dv is equal to uv minus integral v du. And so what we have here, we have this x ex, we want to write this as a u dv. And the way to do that, of course, is u equal x ex dx, sorry. And the way to do this is, remember, another way of calling this is I late. And this is, I late is a scale that says what is u and what is dv. If you don't know what I mean here, let me explain it very, very quickly. So what are the I stands for? The I in I late. These are abbreviations, right? The I stands for inverse trig, L stands for log, A for algebraic, T for trig, and E for exponential. So inverse trig, log, algebraic, trig, and exponential. So what we have here is an exponential, an algebraic and an exponential. So this x is algebraic and the ex is exponential. And the scale, as I said, the one is on top, the x, becomes the u, and the one is on bottom becomes a dv. So u is x, and dv is ex dx, of course, don't forget the dx. Once you have made this choice based on this isolate pattern, you have to find the other guys. So du is dx, and v is the end derivative of ex, which is ex. And then you plug this whole thing into this formula. So now that is equal to u times v, that is x ex, u times v, minus v du, that is ex, and du is just dx, and that's easy to derive, ex. Remember, there's always an extra integration step that has to be done, and that is just ex plus a constant. All right, so this is x ex minus ex plus a constant. Sometimes people take these two terms together. Let's do this now too. Okay, well, this is of course minus 1 over u. We would like to solve for u, right? We need an explicit form, and that is a bit more problematic here because we really need u, because we need to plug it in here. So we need u. So we have to solve for u here, but that again is not so hard. That is that u is equal to minus 1 x minus 1 ex plus a constant. Okay. Now, again, we said that we can take the constant in this kind of method. It suffices to find a single solution. So we can take C what we want to be. So let's take C equal to 0 here. So take C equal to 0. We're only looking for one single solution. Remember, that's how it works. No, I shouldn't say that. I'm sorry. I shouldn't say that. I apologize. Let me not say that. It's not because we're not doing. I apologize. We're looking for all solutions, so we should keep the C here. So what is our solution? Now be careful. Is this a solution? No. This is the solution. So it is y is equal to minus ex over x minus x ex plus c. This is my solution, and then again, to find c, we have to then find initial conditions that would determine what c is. Okay, so that's how this technique works. Now you can manipulate this equation a little bit, but I'm not going to care too much about that. That's not what this is about. So this is the first type, Bernoulli equations. The second type that I'm going to look at is, it's a little bit annoying here. The terminology is very annoying. These are called homogeneous nonlinear equations. But homogeneous means something totally different here, so I'm not going to use that word. And I'm going to just simply say it's a differential equation of this type. So this is a special type, which I'm not going to give a name because the name is so confusing that I better not give it a name. The special type is, it is a function, in general it's a function of x and y. I'm saying it's actually a function of y over x. Okay, so let's give an example here right away. Suppose we have this function here, y prime is equal to y plus x over e minus y over x divided by x. So I don't see how this is a function of y over x. There's a y, there's an x. Okay, there's a y over x there, but there are also y's and x's here. Yeah, in order to see that it is of this form, you have to sometimes do some algebra. So let's divide out every term by x. Remember, dividing in the sum means dividing here and dividing there, right? Okay, so that gives me y over x plus, now the x's cancel, e to the minus y over x. Now I see this form that we said we're gonna have. Okay, so that's an example of such a special type equation. And in that special type, we're gonna do solution. We're gonna simply say, okay, let's make this our new function, u. So this is going to be our, we're going to try to find u here. So of course we're going to solve this. This is y is equal to u times x. So and u is again a function of x. Depends on x. Well, clearly it depends on x, but I'm going to think of it as a function that just depends on x. As I wrote it down, it depends on y and x, but y also implicitly depends on x. So, okay. So what does that mean now? Is let's solve this equation, right? Let's solve this equation here. Well, we're going to plug this in. Okay. Now remember, this is actually this. So what do we get? We get y prime, that's ux prime, is equal to, well, and here we have the form already where everything is written in terms of y over x. So this is u plus e to the minus u, right? I'm just plugging in, I'm using this plug-in here for these two guys. This is just u, this is u, this is u. Now, of course, on this side, I have an actual y here. Here, sorry, where is my y? Here, this is an actual y, so I have to write it this way. So I have to do the product rule here. So that's u prime, derivative of the first, copy the second, plus take the first, copy the first, take the derivative of the second, which is 1, is equal to u plus e minus u. The u's cancel. This doesn't have to happen, but it happens here. So we're lucky, but it doesn't have to happen. We get u prime x equals e to the minus u. Now remember, again, this solution is separating, we want to get to a separable variable. Separating the variables to an equation, a separable equation. And this is again the prime. So my prime is a little bit high here, right? My prime was, okay. So again, this is what we want, right? So this is, if I bring this to the other side, it would be eu du equals 1 over x dx. If you don't see this right away, stop the video and do the calculation for yourself that this is the same as what I wrote down above, but separating the variables. So now I can integrate. The end derivative of eu is eu. The end derivative is ln of x plus a constant. I said, sorry, we have to keep the constant here again. We have to solve for u. Remember, because I'm going to have to plug this in here, right? So this is my solution here, this one. So I'm going to have to plug, I need to know what u is, not eu. But that's not a problem. How do you get rid of this? Again, each time when I ask a question, just pause the video. If you don't know it right away, pause the video and think a little bit about it. Okay? So the answer, of course, is take logarithms. So take ln's of both sides. You get u equals the ln of x plus c. Well, why not? Ln of an ln exists. It's actually called the bilog. It's used. It comes often occurs often. Okay, so the solution. So our solution is, again, be careful. U is not a solution. Y is u times x. So x ln of x plus c is our solution. And just for the heck of it, let's do an let's do a special initial value problem. So suppose that where was my equation? This was the equation. So I'm adding now, and I want it to be, now we have to be careful. I cannot ask something to happen at 0 because we are talking about fractions y over x. I'm dividing by x. So I have to say something like y over 1 is 2. That's my initial condition. Say. Again, where does it come from? I don't know. I just made this up. Okay? So for the initial condition, now I have plug in x equals 1 in this equation. Then this becomes 2. This is 1. This is the ln of 1 plus... the ln of 1 is 0 plus c. So we see that 2 is the ln of c. So c is the e of e square. And so my solution for the initial value problem is x ln x plus e square. And there we are. And that's how we solve these things. Let's do another example. So once you know this technique, it's really not so hard. You have to recognize the form. That's going to be a little bit the tougher part, is recognizing which special type, which form you are, so that you can separate the variables. So we had the Bernoulli. What was Bernoulli? Well, Bernoulli looked very much similar as a linear equation, except we had an extra power of y here. But nothing more complicated than that. Okay? Then we have this special type, is where everything can be written in terms of y over x. Now, this might not always be obvious. It was not already obvious in this case, but it's even perhaps less obvious in the following one. X squared y prime equals y squared plus xy minus x squared. And let's do again, I'm going to from the start now do initial problem. y1 is 2, initial condition problem. Why is this of the form that I'm saying? Well, let's see. Let's try to write it this way. We have to write y prime as a function of y divided by x. So first of all, we should solve for y prime. So this y squared divided by x squared plus xy divided by x squared plus minus x squared divided by x squared. Why don't we put this on common denominator? Well, I want to show you that we have y-axis, and this is much easier if I do it this way. Now we have here y over x squared plus one of the x's cancel, y over x, and here the x squares cancel, minus 1. So by this little manipulation, I got immediately what I wanted. Okay? So how we solve this now? Remember, we're going to put y over x equal to u, which means that y is equal to u times x. So if I plug this into this equation, on the right hand side I get u prime x plus u, remember that's the derivative of the product, equals, I skipped one step, but again, pause the video, go look it up, go scroll back or figure it out for yourself. This is what it is if you derive y. And when you get on the right hand side? Well, you plug in just, now I use this one, u squared plus u minus 1. Okay, the u's cancel here again, but as I said, this kind of cancellation, there's some cancellation, sometimes there's nothing. Okay, so we get u prime x is u squared minus 1, so this means that, separating variables, right? So we're going to separate the variables, keep an eye on what we need to do. That means we have to write du over u squared minus 1 equals 1 over x dx. We have again u squared minus 1. Remember that was we had to partial fraction decomposition. So we know that 1 over u squared minus 1 is the same as a half, let me write it this way, sorry, is 1 over 2 u minus 1 minus 1 over 2 u plus 1. Again, where this comes from, you have to check it yourself that this is exactly what happens, okay? And so, all right, so this integral becomes a half u minus 1 du integrating minus a half u plus 1 du, and the integral on the left hand side, let me just write it up, that of course is just ln x plus c, and here we get a half ln u minus 1 minus a half ln u plus 1, okay, that is equal to a half ln u minus 1 over u plus 1. Remember, if you're subtracting ln's, then that is what happens. They divide the inside parts. And what about this half? Well, the half that again is a rule of exponents. This is the same as the ln of u minus 1 over u plus 1 to the power a half, which means just radical. Okay, and that is equal to ln x plus c. We want to get rid of the ln's, so we have to take e, the exponential of both sides, so that will give me u minus 1 over u plus what? Now, half I'm going to write just as a radical, that is this half, right? And here we take also, so we take the x above both sides, that would be e ln x plus c, that is e ln x times ec, but e ln x is just x and ec is just a constant, d. So d is a constant. So again, I renamed the constant here. So what we see is that we get this equation. Now we have to still solve for u, so we have to square both sides. So u minus 1, so square u minus 1, u plus 1 equals d squared x squared. Now we could replace d squared by some constant, but let's keep going. And we have to solve for u, so by cross multiply, and then bring the u terms on one side, and the non-u terms at the other side. Okay, so I multiplied this out and brought this to the other side, and I brought this to the other side and multiplied this out. Okay, so that means that u1 minus d squared x squared equals d squared x squared plus 1. So finally we see that u is equal to d squared x squared plus 1 over d 1 minus d squared x squared. So I guess, let me write it a little bit nicer, more symmetric. 1 plus d squared x squared over 1 minus d squared x squared. So is that the solution? No, remember it is u times x. So the solution is x times 1 plus d squared x squared over 1 minus d squared x squared. That is our general solution, but we have an initial condition. Where did it go? Here. y1 equals 2. So now x is 1, y is 2. So I'm going to plug that in here. So 2 equals 1 times 1 plus d squared over 1 minus d squared. I did this here, but I already mentioned last time, why don't you plug it in here? Because it's the same, nothing has changed here, we just rearranged the terms. It's the same equation. So let's plug it in here. Okay, sorry. If I plug it in here, then I see that u minus 1, what am I saying? Oh, no, I have to be careful now. I'm sorry, no, I cannot do that. I apologize. No, because this is not the same equation as this equation. I apologize, it is not. Why is this wrong? Well, I said, well, it's not the same equation because this has an extra x in there. Okay, so I cannot use this equation. This is a different equation, so I have to plug it in the actual equation. Sorry about that. So what we have here is correct. Okay, so this is correct, and this is not correct, so let's go the way. So this is what we have to do, and now we have to solve for d. It's a bit tedious. Let me see here. Okay, they say, okay, we solve for this. Now, remember, d squared, let's call this, it's annoying that I have written d squared. I should have, from the beginning, just renamed this as a variable just by another c or something like that. But okay, I've stuck down with this, let's go on. So cross multiply 2 minus 2d squared equals 1 plus d squared. And so we see that 1 equals 3d squared, so we see that d squared is equal to 1/3. And this, we don't need d, I need d squared, right? So that's why it's a bit silly of me to keep the d squared here. I should have, so what better would have been say, okay, I'm introducing a new constant, let's call it ax squared, and then carry out the calculation with a, and so we would have found y is x 1 plus ax squared over 1 minus ax squared, and then this would have been 1 plus a squared over 1 minus a squared. So no squares anymore, sorry, sorry about that. The whole point is not to get the squares, right? Okay, so I'm going to do this. Let me do the calculation over with the a now. Okay. So I hope that you see that this is what you get if you replace d squared by a. Well, let's just plug it in. So let's work now with this one here. So we see that 2 is equal to 1 times 1 plus a over 1 minus a. So there's 2 times 1 minus a is 1 plus a. So 2 minus 2a is 1 plus a. So that means 1 is equal to 3a, and so that a is 1/3. So our solution is y equals x, 1 plus 1/3 x squared over 1 minus 1/3 x squared. And that's our solution. Now, you know that you can actually always check your answer. There are two things you should check. First of all, that this satisfies the differential equation, the original differential equation. So does this satisfy this? Because it's a little bit of work, right? You're gonna taking derivatives and so it's not hard. It's just going to be a little bit of algebra here because you get here fractions and so you get the quotient rule. So it is a bit ugly to do, but it is possible to do. But you have to check, of course. The second thing is that this function satisfies the initial condition. If I plug in x equals 1, then do I get actually y equals 2, right? Do I have this initial condition? But in principle, so we can check these things. But of course, that's sometimes very time consuming. So how do you recognize that this was of this case here? And I'm going to say this now, but I'm going to not write it down because I don't want to confuse you. This is where the term homogeneous, sometimes called these homogeneous ones, although they are not homogeneous in the sense of linear first order equations, this is homogeneous because this is an expression in which each term has the same degree. Degree 2, degree 2, degree 2. And this one also has degree 2. Okay? So in other words, if you have something of the form, a special form would be P y prime equals Q, where P and Q have the same degree. It doesn't have to be 2. So the same degree in x and y, in x and y. So we have to calculate the degrees in both. Okay? So this means, this is why I say this has degree 2, right? Degree 1 in x, degree 1 in y, so the total degree is 2. Okay? If you have something of this form, then I claim you can always write it, then it's of this special type. So just to give an example here, suppose we have, I'm not going to work it out, I just want to show you this how because you're going to probably have to do this in the homeworks. If you have something of the form, let's say 3x cubed plus 4xy squared y prime equals 5x cubed minus 2y cubed, that is of this special form because, let's see, because you see, this has degree 3 and this has degree 3. Let's see why it is of this form. So let's work this out here. So I'm going to bring this to this side. So now, oh, Professor, how are we going to do this division here? Now we have a sum in the bottom too. True. So what I'm going to do now, to show that it is of the form that I want, I'm going to have to divide top and bottom, numerator and denominator, by x cubed. The cube comes from the fact that it's degree 3. Let's see what we get here if I do this. So I'll write it here in red. So I divide here by x cubed, I divide here by x cubed, divide by x cubed. Remember, this divide top and bottom means divide every single term by x cubed. And let's see what this happens after cancellation. We get 5 minus 2 y over x cubed. I combine this as a single cube, this one. Okay, here the cubes cancel again. 3 plus 4. One of the x's cancel and I get y over x squared. And here you see that, so this is, now you see that it just depends on y over x. And so if you want to solve this, it's going to be horrible to solve, but I'm just saying, what should we do? Remember, we do this, we replace y over x by u, and so we would get here on the left hand side, we get u prime x plus u equals 5 minus u cubed over 3 plus 4u squared. Now, this is a polynomial. There's a u here still, so this is a rational function. In principle, we can derive this thing, right? We're gonna separate the variables here, so it gets really, really ugly, but it is in principle possible. Now, the homework problems or the quiz problems were always cases where you actually can do this. Okay, that's enough for this section. And then please do the homeworks on it, and there will be, of course, quizzes.